You know, we hear about atoms all the time, but have you ever stopped to think about where the real action is? It's not in those electrons zipping around. Nope. The real power, the deep mystery, is locked away right in the center, in the nucleus. And today, we are going to crack it open and see what makes it tick, from what makes the sun burn to what keeps our lights on.
So let me ask you something right off the bat. What do you think is the most powerful force in the entire universe? I mean, the strongest one there is. The answer is hiding inside the atom. And stick with me, because by the end of this, you're going to know exactly what it is.
All right, let's dive right in. We're going to zoom way, way in, past all those electrons and get to the very heart of the matter, the atomic nucleus.
So, what is the nucleus? Well, it's this ridiculously tiny, super dense core right at the center of the atom. And when I say tiny, I mean it's almost impossible to wrap your head around how small it is. But here's the kicker. It contains practically all of the atom's mass. And it's made up of two main players, which scientists call nucleons. First up, you've got your protons. These little guys have a positive charge, and their number is everything. It literally defines the element. Got 6 protons? That's carbon. Always. Got 92? That's uranium. Simple as that. Then you have the neutrons. They're the neutral ones, no charge at all. Think of them as the heavy buddies that just hang out, adding mass, and, this is super important, keeping things stable. Okay, so this is where things get really interesting. You've got all these protons, right? All positively charged, all crammed into this impossibly tiny space. Now, basic physics 101 tells us that like charges repel. So, they should be trying to fly away from each other with a violent force. Why doesn't the entire nucleus just, blow itself apart? Well, the answer to that little paradox is also the answer to my first question. It's time to introduce you to the strongest glue in the entire universe. This force, which holds the nucleus together, is called the strong nuclear force. And the name does not disappoint. We're talking about a force that's 100 times stronger than the electromagnetic force that's trying to rip those protons apart. 100 times. It is, without a doubt, the heavyweight champion of all the forces in nature. The best way to think about it is like a kind of cosmic super glue. But it has one weird rule. It only works over incredibly short distances. I mean, really short. It's only powerful inside the tiny space of the nucleus. Step 1 foot outside that boundary and its power just vanishes. Poof, gone. So this incredible force creates something scientists call binding energy. It's literally the energy that binds the nucleus together. And here is where your brain might start to melt a little bit. If you take a nucleus and weigh it, then you pull out all the protons and neutrons and weigh them separately, the separate parts actually weigh more than the whole thing. So where did that mass go? That missing mass, or mass defect, wasn't lost. It was converted into the pure energy that's holding the whole thing together. And yep, you guessed it, this is exactly where Einstein's famous equation E equals mc squared comes into play. It tells us that mass and energy are basically interchangeable. That tiny little bit of missing mass gets converted into a huge amount of binding energy. How huge? Let's just say converting a single gram of mass into energy would be like burning millions of pounds of coal. It's an insane amount of power from a tiny amount of matter. Okay, so we know this incredible energy is locked inside the nucleus. The big question is, how do we get it out? Well, that happens through two very famous processes: fission and fusion. So let's break these down. First, there's fission. Think splitting. You take a big, heavy, kind of wobbly nucleus, like uranium-235, you smack it with a neutron, and it splits apart into smaller pieces. This split releases a ton of energy and more neutrons, which can then go and split other atoms, creating a chain reaction. Then you have fusion. This is the complete opposite. Think combining. Here, you take two superlight nuclei, like hydrogen, and you force them together under insane heat and pressure. They fuse to form a heavier one. This is what powers the sun, and believe it or not, it releases even more energy than fission does. So, why should you care about any of this? Well, fission? That's the science that's powering our electrical grids right now. Every single nuclear power plant on the planet uses fission. It's how we turn the physics of the atom into the light in your home. Fusion, though, that's the holy grail. It's the big dream. If we could figure out how to build a mini sun here on Earth to control fusion, we'd have a source of clean, safe, and basically limitless energy. It's one of the greatest scientific and engineering challenges we've ever faced. But wow, the payoff would be incredible. But here's the thing, not all atomic nuclei are built the same. Some of them are unstable, and that brings us to two really important ideas: isotopes and radioactivity.
Remember how the number of protons defines an element? Well, you can have atoms of the same element that have a different number of neutrons. These different versions are called isotopes. So, they're all the same element chemically, but their nuclei have different weights. And, crucially, some are rock-solid stable, while others, not so much.
A perfect example is carbon. The most common type, carbon-12, has 6 protons and 6 neutrons. It's perfectly balanced and stable. But then you have its isotope, carbon-14. It still has 6 protons, so it's still carbon, but it has 8 neutrons. That little imbalance, those 2 extra neutrons, is enough to make its nucleus unstable, and that means it's radioactive.
And that's all radioactivity really is. It's just an unstable nucleus trying to chill out and find a more stable state. To do that, it spontaneously falls apart, or decays, by spitting out little bits of energy and particles until it settles down into something more balanced.
Now, this might sound a little scary, but this natural decay process is actually incredibly useful to us. We use the super predictable decay of carbon-14 to figure out how old ancient artifacts are. That's carbon dating. And in medicine, it's a total game changer. We use radioactive isotopes in things like PET scans to literally see what's happening inside our bodies, and in radiation therapy to zero in on and destroy cancer cells. So when you step back and look at the big picture, it's pretty staggering. All this physics happening in a space too small to even imagine. It's what powers the stars, it's what powers our world, and it's what helps us save lives. The atomic nucleus really does shape, well, everything. And that leaves us with a huge question for the future. We've mastered fission, splitting the atom. And we're on the cusp of maybe, just maybe, mastering fusion, replicating the power of a star. So as we look forward, what do you think is the real future of energy? Fission or fusion?